Hello, in today's video I'd like to share what I learned by applying simulated annealing to the traveling salesman problem. SA is a powerful yet simple classical AI optimization algorithm for solving many types of problems. I discovered that results using the plain vanilla out-of-the-box implementation of the algorithm are very good, but can be even better after applying some tweaks and enhancements. These were some of the ideas I came up with. Most of them worked, some did not. I'm sure there are many others that can be tried. On this slide, you can see some artifacts of SA, particularly as they apply to the TSP. So you can see, for example, this is the network that we're going to work on through the examples and the shortest path that's been found so far. Here's a cooling rate that can be applied, and the cooling rate is important to the acceptance probability of accepting the next move that we should take in terms of changing this network. Here's a typical curve of the distance shrinkage through the iterations. As you can see at the start, we're rapidly making improvements, and then towards the end becomes more difficult. But let's go on and see what we can learn about making simulated annealing applied to traveling salesmen even better. So before we can talk about the algorithm itself, let's focus on the metaphor used here. So it's going to be about the natural or the physical process of annealing, which is the slow cooling of molten material to deliver the desired properties of that material that we want. So with gradual cooling, springs become flexible, glass becomes less heat sensitive, and rock crystals grow. Simulated annealing is inspired by the slow cooling metaphor. All right, let's talk about simulated annealing in a nutshell then. So as we already learned, it's a classical AI search algorithm inspired by thermal annealing to find very good tours efficiently for near optimality. Not guaranteed most of the time. The application useful in large, discrete, highly constrained optimization problems where local moves are meaningful. We can tune it through hyperparameters that offer a trade-off between speed and quality. It's highly flexible, suitable for a wide range of problems. For example, it's been used in the areas of logistics and scheduling, design, layout of circuit boards, resource allocation of a supply chain, and you can even use it to find hyperparameters that should be used in the algorithm itself. It's stochastic in nature. So for example, if we run it once, we may get an answer on a problem. You run it again, it could give you a different result. It works well in hierarchy topology. So if we have lots of local minima, the algorithm's pretty good at finding its way out of those. The implementation, as we'll see soon in the algorithm I'm going to show you, it's very simple. And all we need is a cost function and a tweak operator for the next move. We don't need to calculate the derivative of something or understand what a function is of this particular process. All what we have to do is to develop a fitness function and an ability to calculate a slight perturbation of the current state. And because of these, it's able to hill climb out of poor solutions. So the idea that we can, at the start, wander widely and then settle wisely to find our best answer. So this is all there is to the algorithm itself. Let's walk through it. So at the start, all what we have to do is to generate an initial solution. If we think about the traveling salesman, where we have a bunch of cities to visit, each city is visited each and only once. And we close the loop again by going back to the original city. All what we need to do is come up with an initial guess. It could be a total random order of these towns. And from that, we have to calculate the fitness. What was the total distance of that path? Now here's the key. We need to perform a perturbation of that path. One move, like, hey, let's swap the order of two of these towns, or let's move one town in front of another town. So we'll get into the details of that and compute the fitness of that change. So again, we have the original tour, we tweaked it a little bit, let's calculate the fitness of the new tour. Now we have to get into this idea about, are we going to accept the new tour, the new candidate, as the current tour? And there's going to be a method here where if it's better, we're always going to accept it. If it's not an improvement, we may accept it. And we'll get into the details here in a little bit. So if we do accept it, we're going to then, the candidate becomes the new current, and we reduce the temperature. So this temperature down here is important because it's going to determine the rate of acceptance of a candidate that was worse than the current. And we'll show you an example of this as well. Have we met stopping criteria? Yes or no? Stopping criteria could be the number of iterations, the final temperature we've reached, has the network changed recently, and so forth. And if we're not there, we go back up to perform a tweak, and we keep running through this network here, this loop, until we finally say that our stopping conditions have been met. Let's talk about this notion of candidate acceptance, and that's related to the temperature of our current state. The algorithm starts at a high temperature and then goes to a low temperature, and that rate at which it goes to the low temperature is going to be a function of alpha. These are constant percentage declines. As you can see, with a smaller alpha, we decline faster compared to one, for example, 0.999 here, gradual, and then the 99 alpha is going to be steeper. It's the temperature that's going to determine the acceptance rate of a worse candidate. A better one is always accepted. And so with a worse candidate, let's work through an example related to temperature. Let's say the delta is 50. So we have a positive 50 units worse of the current candidate relative to our best. So should we accept it? Well, if the temperature is high at 100, let's say, and we do this math here of E minus D, D's delta divided by T temperature, we're going to come up with its acceptance rate of 60%. So more often, we're still going to accept a worse outcome because at the start, what we want to do is explore, is expand the solution space and explore. However, as the temperature begins to cool, that acceptance is going to become less likely. So when T is equal to 20, we go over here to our acceptance chart here with our probability zones here. We could see here that T20, delta 50, and we're here at about 8%. So a much less likely chance of acceptance, as towards the end, we just want to keep on accepting better and limit the exploration. So with high temperature, early on encourages exploration, but as it cools, exploitation becomes more prevalent by accepting only the better ones. Making tweaks or changes to the current candidate is a critical part of the algorithm. So for traveling salesmen, we can think about many operators that can do this. So think about like a switchboard where we have this network, and in the old days, an operator would sit there and change the network to make a phone call go through. So that's what we want to do here. We want to change this network slightly, and there's different operators that can do this. We can think about a flip, where if our original network was a sequence of numbers, let's say we had 8, and all we're doing is flipping 3 and 2, for example, or a swap, where we're going to put 2 in the 6 spot and 6 in the 2 spot. Then we have something called 2-opt. It's like flip, but works with 2 at a time. You can see here, we're going to flip 1 and 2, flip 3 and 4, and then reverse those 2 pairs. Then we're going to do a transport move of just 1. For example, move 7 over here to where 3 used to be, and the rest of them just get pushed back. Do the same thing with 2 of them, and then with 3 of them. So these are the operators that we can use to perform tweaks. And it's important that these are subtle perturbations, not massive changes to the network. Tran 3 is probably the biggest massive change that we'd ever want to do, because if we're doing a massive change, then the algorithm kind of reverts into a Monte Carlo search, which is what we don't want. We want it to build upon gradual improvements so that it can effectively explore the solution space, but not be jumping point to point, and where we can't dive deeper, or I should say climb hills more effectively in our solution space. So let's apply this to a real-world, very well-known traveling salesman problem, and that's going to be the 127 beer gardens in Augsburg, Germany. A lot of fun. I like to brew beer myself, and so I'm into beer, and I thought, okay, this is going to be a great one for us to explore. All right, so we have chosen our 127 beer gardens in Augsburg. We have Heinz and Hilda here that need to find the shortest path. And by the way, if we think about what this tour is going to look like, it's going to be basically 126 factorial divided by 2, because the network could go in one direction or it could go in the other direction. And then so what that turns into is there are 10 to the 212 possible different tours. That's just a huge, amazing number of tours if you were trying to solve this in a brute force method. The known shortest path is a distance of 118,282 units. I'm not sure what that is, if it's meters or what, that might be it. But let's see how close we can come with some of these optimization enhancements that I talked about. So here are the enhancement strategies that I came up with. First one's really simple. Because the algorithm's stochastic, let's just run it multiple times. So if we run it 10 times, we should be at least as good an answer as just running it once. Then instead of using default values for starting temperature, ending temperature, and alpha, let's run some trials on our particular problem and see which works best. Then there's preconditioning. We don't have to start with a random network. We can start with one that's sort of good. If we came up with a greedy algorithm, for example, that gave us a good start launching point, the assay should perform better. Then there's restart. Along the way, for example, let's say as we cool our temperature rate, we've decreased our candidate acceptance, and we're finding there's a really long time between an accepted candidate. Let's go back to the last known accepted candidate and restart from there. So raise the temperature back to that condition, and let's see if we can continue our exploration. Reheat is sort of a similar idea, but instead of going back to the last known accepted, we're going to just raise the temperature from where we currently are and see if that raising is going to encourage more acceptance. Then there's multiple tweaks. Use a diverse set of neighborhood operators for structural improvements. Dynamic tweak probability, so rather than sort of a constant acceptance rate for each one of the 6, if we have 6 different operators, we could look at the statistics as we go through the iterations and note recently which one has performed the best, and keep using that one in sort of the redistribution of those probabilities for using the operators. And finally, competitive neighborhood search. So rather than running one tweak and then doing the candidate acceptance evaluation on the one, let's run 5 or 6. And then the best candidate of those, in terms of the delta with the current, let's choose that as the go forward candidate. All right, so here's run essay multiple times. So on the right, we can see the best tour of 100 trials. And we came up with a distance of 119,282. Wow, that's pretty good. Remember, the best was somewhere 118,000. So we are within 1% of the known best. If we just took the first tour of that 100 batch, we came up with 124. And you could see that although there's a lot of similarities between the two of them, you can also find places where, for example, here compared to here, and then here compared to here, you can see why this tour is going to be slightly longer than this one. And that's just from running the stochastic algorithm multiple times. So here's preconditioning with pre-sort. So here's our random start. So you see here the distance for random start is quite huge. As you can see, a lot of blue lines going back and forth, 612,000. But if we did sort of a greedy algorithm by starting at a particular node and saying, okay, which one's the closest? Accept that node, draw a line between them, find the next closest one to that, and so forth. This would be then called greedy pre-sorting. We can come up with already a great distance reduction, and we're down to 136,000 as our starting point. All right, let's look at that. So pre-sort, let's call that low entropy. Random order is going to be high entropy. If we looked at 100 runs, the first case is going to be we capped off at 50,000 iterations. You can see here the difference then. High entropy, that's the random, preconditioned red, and you can even visually see from the 100 runs which runs are going to be, or which set is going to be the improvement. And our p-value indicates that these are markedly different sets, where the pre-sort low entropy was obviously the better choice. What happens if we expanded it out to 200,000 iterations? Same kind of deal, still a very massively low p-value, and we still have at least 1,000 units of improvement by using the pre-sort. Let's try to put an improvement on top of pre-sort and see if that does an even better job. So this one is called bow tie removal, or we're going to look at something called 2-op swap. So here's this bow tie. So we can see here that wherever we have a cross in the lines, there's an opportunity for improvement. So if we can come up with an algorithm to identify these crossovers, eliminate that, as done here, we've shortened the distance. So we went from 136,000 to 132,000. Let's see if that helped our improvement. So we ran 100 trials here of greedy pre-sorting with and without the 2-op swap. You can see here, this is the blue has it with that bow tie removal, the red does not. But in actuality, our p-value is kind of above our cutoff of 0.05. So we're going to say that these sets are really the same, and there's no benefit to doing this. So really, maybe the 2-op swap is something that SA would have done anyway, regardless. And so it wasn't useful as a determiner for our initial starting point. Here's the idea of restart. With and without, so blue is going to be with restart applied, red without, and we can see these are markedly different distributions, either if we began from a random tour or if we began from pre-sort tour. Interestingly, from a random made a bigger difference than from pre-sort. I guess there was maybe less room for improvement, so the difference is going to be smaller, but at any rate, under both scenarios, using restart after 5,000 iterations of no acceptance was beneficial. Here's reheat, same idea. So raise the temperature to increase acceptance rate after 500 iterations without acceptance. And we could see that, again, there's markedly difference in these distribution with the reheat applied being the better choice with a random or with a pre-sort tour. The next one was dynamic operator probability. So using prior acceptance rate to adjust the operator probability of occurrence. Temperature regimes may favor different likelihood of move operators. Unfortunately for this one, it turned out that when we looked at with and without the dynamic probability adjustment, the p-value was above 0.05, like it was between 0.23 and 0.33. So we can't really say this is going to be useful. And if we look through the graph through the iterations, we can see that there doesn't really appear to be, although the orange, what's the orange? Flip occasionally popped out. It wasn't consistently, or in different temperature regimes, you can see a marked difference between one or the other. So unfortunately, this tweak strategy didn't prove that useful. Let's talk about local neighborhood search. So if you remember from the algorithm back a few slides ago, here's the basic SA, what we were doing. What we're going to do with SA with neighborhood exploration, we're going to perform, instead of one tweak, we're going to perform several, compute the fitness of all of those candidates, keep the best candidate, and then move forward with acceptance. So let's see what that did. And this one turned out to be actually quite useful. We can see here again without and with the K5. In this case, we looked at 5 different tweaks at the same time for acceptance. And we did much better, as you can see through our final distance rate, as opposed to without. And that was even after a high entropy start or a low entropy start, same kind of deal. So this one definitely proved to be useful. Now the algorithm did run longer, almost 5 times as much, but I think the results more than justify doing that. All right, let's go ahead and tune this thing. And so rather than getting fancy and using SA as an algorithm to find the best hyperparameter set, let's just do an exhaustive search of the 3. So starting and ending temperature and alpha, run a bunch of trials, see which comes up. And it looks like the best configuration is going to be a start of 500 and end temperature of 0.001, and then this degree of alpha 0.999. It's interesting that you can't look at these individual things in isolation. They're all interrelated. So it becomes very difficult to separate the ones, but you have to look at it as a combination effect. But so most of my trials I did run with this configuration. This chart shows operator performance if I ran them in isolation, so only flip, only swap, and so forth, or if I ran them all together. It's interesting that only 2-opt actually did better than all with an initial random start, the high entropy start. So you see the mean, the min, max, and then how many new bests were found. So that was the high entropy start. And then this is low entropy start. So again, 2-opt by itself seemed to do slightly better than if I used all of them combined in terms of the mean. However, when we look at in combined with a local neighborhood search, low and high entropy, all performed slightly better than 2-opt. So that would be my recommendation, to use a wide range of operator tweaks as opposed to relying on just 1 or 2. And again, here's where it comes down to, it's hard to look at these in isolation. We have to look at them with the different hyperparameter adjustment, with the different tweaks or enhancements that we're doing. What is the overall best combination of things that we should do to improve the performance? So as you can imagine, with these enhancements and tuning that I talked about, it's very easy to get twisted off, just run plain Jane kind of SA, accept the defaults and run it, and be kind of disappointed in my outcome. As you can see here, this is kind of the untuned range. It's even worse in our original preconditioned start, which averaged around 136,000 if I remember right. So you do have to apply some care. It's not impossible, but with care comes results. So if we did do the local neighborhood search, the preconditioning, better starting temperature, and this restart and reheat, you come up with a narrow, very good acceptable range here that's actually very close to the ideal of 118,000. So tuning is indeed critical to success when using SA. So here's what I learned: effective enhancement strategies. So the greedy preconditioning, the local neighborhood search, have a low alpha, a low ending temperature, high starting temperature, especially in regions of high entropy starts. Restart and reheat seem to be effective. Do multiple independent runs, using multiple operators for a richer moveset to improve the landscape search. The things that didn't work so well were the dynamic operator probabilities, preconditioning, the conditioning, as it were, with the 2-opt swap. And here's some key takeaways as well. So I'd say that the stochastic nature of SA requires multiple independent runs. The hyperparameters, the enhancements, it's all interrelated, as I mentioned before. Strong precondition is helpful. Rich move sets or tweaks, also useful, but remember, keep them small. Don't have it turn into a Monte Carlo start search type search, I should say. SA excels at exploration, but local search delivers the final structural improvements. And finally, understand your quality goals versus your time budget. you can always have it come up with a better answer through increased time. The question is, how much time are you willing to wait? So I found this very useful myself. There were some aha ones that I was actually surprised it worked or didn't work. And I hope you got the benefit from this too. So this was just a simple approach to the classic traveling salesman problem. Next video, what I want to do is apply this essay to scheduling and routing. And we could see what are some enhancement strategies that works effective with those. So I thank you for your time.